This chapter deals with changes in state. You probably already know that there are four states of matter. You're probably familiar with three anyway: solid, liquid, gas, and also plasma. So if we take H2O, water, as an example, the solid phase we call ice. We add heat energy to that. It breaks down the rigid structure of the molecules, the particles that make up the ice, breaks it down into water. If we add still heat energy, then the molecules get moving faster and their structure gets broken down further, and we get the gas. And if we add energy further, the molecules can actually break down into things called ions and electrons, and that state of matter is known as plasma. We're not going to be doing very much with that at all. Okay, now, evaporation. Evaporation is when a liquid gets transferred gradually into a vapor or a gas. And it's basically a cooling process. And the reason why that is that the molecules that constitute the liquid have an average kinetic energy that's dependent upon what their temperature is. So that means that some of the molecules have very high kinetic energy, some of them have low kinetic energy, some somewhere in the middle. Well, some of the ones that have high kinetic energy can actually escape the liquid, and as they do that, they go into the gaseous phase. But since you are losing some of the molecules that have high kinetic energy, that does reduce the temperature of a liquid a little bit. And so, in general, as a liquid evaporates, it tends to be a cooling process. The temperature drops gradually. Now, you're probably familiar with that. You take a little alcohol, you put it on your hand, you can feel it very cold. It evaporates very quickly. Or you step out of a shower while you're still wet into a room. You get chilled, or come out of a lake. You tend to get chilled because the water immediately starts to evaporate and it cools you down. Okay, now the opposite of evaporation is condensation. And just like evaporation was a cooling process, condensation is a warming process. And condensation is when you have molecules of the vapor being transformed back into the liquid. And as they do that, the liquid is absorbing these molecules that have a relatively high kinetic energy, and that brings the temperature up in the liquid. One of the places we're very familiar with that is with humidity. In the summer, the humidity, the relative humidity, tells us the percentage of water vapor in the air. And when that gets high, we start to get some condensation, particularly if the temperature is up a little bit and you start to perspire. These water molecules tend to start to condense on the perspiration, actually making it warmer and making you, as a result, warmer as well. Okay, now boiling is when we take a liquid and we add heat energy to it and it gets converted to a gas. And I'm sure you've probably all watched the boiling process. You put a pot on the stove and turn the water up, turn the gas up, or the heat up, I should say. And you see these, after a while, you see these little bubbles forming on the bottom. And these little bubbles is bubbles of vapor that are forming where it's most warm. And as they begin to rise to the top, they'll collapse because they get into the cooler water. But as the water tends to get uniformly warm, these bubbles of vapor tend to be able to exist all the way to the top. And when they do that, we say that the liquid is boiling. So a formal definition of boiling point is the temperature at which the vapor pressure, that's the pressure of these little vapor bubbles, can exceed atmospheric pressure. So, for example, if you go up to like Denver, for example, the mile-high city, where the atmospheric pressure is somewhat less, the boiling point of water tends to drop because the vapor pressure is not required to get so high as it does down at sea level. Okay, now just sort of a review here of energy changes when you go from a solid to a liquid to a gas. If you want to transform a solid to a liquid, then heat energy has to be added to the solid to convert it to the liquid. And when you go from a liquid to a gas, heat energy has to be added to the liquid in order to convert it to the gaseous phase. On the other hand, if you go in the other direction, in order for gas to go to the liquid state, then heat energy has to be released from the gas. And from the liquid to the solid, the same thing, heat energy must be released from the liquid in order for it to solidify. Now we're going to look at this phase transition from a solid to a liquid a little bit more closely. There exists something that's called the latent heat of fusion. The latent heat of fusion is defined as the quantity of heat that you have to add to a solid in order to convert it to a liquid, when the solid is already at its melting point. Now, for ice, this quantity is 80 calories per gram, which is 335 joules per gram, same number, only expressed in joules. And that quantity of heat must be absorbed just to cause the change in state from the solid to the liquid. Now, we use this a lot, for example, in keeping drinks warm. If you have a glass of water on a hot day and you want to keep the temperature of the water to be cool, just about 0 degrees Celsius, you can add some ice. And all of the heat that gets absorbed by that glass of water is going to be used to melt the ice. There's not going to be any change in temperature of that liquid until all of the ice melts. Now, when you go from a liquid to a solid, in other words, if you were talking about water back to ice, then this 80 kilocalories per kilogram or calories per gram, however, either one of these is the same, must be released in order to make that transition from the liquid to a solid. And again, there is no accompanying change in temperature when this happens. Now, a similar thing happens when you go from the liquid state to the gaseous state. In this case, it's called the latent heat of vaporization. This is defined as the heat needed to make the transition from the liquid state to the gaseous state when the liquid is already at its boiling point. For water, the value is 540 calories per gram. Quite a big number, by the way. And that much heat must be absorbed by the water to completely convert it into the gas. You can get an appreciation for how big this is if you think about taking a pot of water, putting it on the stove, turning up the heat to it. Doesn't take that long for the water to begin to boil, but think about how long it would take for all of that water to completely boil away into steam. That would take quite a long time. Okay, now, when you go the other direction, when you go from a gas to a liquid, same thing, 540 kilocalories per kilogram or calories per gram must be released by the gas in order to convert it into a liquid. And this, by the way, is the reason why steam burns can be so much more severe than a burn due to hot water, for example. And that's because if you take your arm and you thrust it into some vapor, water vapor, that's at 100 degrees Celsius, when that starts to condense on your arm, it's going to release 540 calories per gram or kilocalories per kilogram of heat, and that's a very large quantity of heat that can cause pretty severe burns.